This is our first video on angular motion and angular velocity, angular acceleration. So I will look with you at how to the definition and how to derive some of the formulas. So we know that linear velocity formula is the distance for displacement over the time and measured in meters per second. For the angular velocity, it's the angle that becomes your distance. So in a circular motion, imagine the wheel. You have a dot here and you have the dot over here. When the dot is moving from this position to this position, so you have, this is the new position of the dot and this is the new position. Let's do them in different colors. So the red dot and the red dot and the purple dot and the purple dot. So the purple dot is moving bigger distance over the same time as the red dot. The red dot moves less distance over the same time, but they move the same angle. So for the angular velocity, I'm going to say angular velocity, it's omega, and it equals to angular, I'm going to call it distance, it's not the right word, but angular distance is going to be the angle. So that is angle over time, and it's measured in radians, angle measured in radians per second. Then for acceleration, we had before linear acceleration is equal to change of the velocity over the time and measured in meters per second squared. Then angular acceleration is going to be the letter alpha and equals to change of the angular velocity over the time and measured in radians per second squared. Just as before, the distance is equal to average velocity times the time and measured in meters. The distance in this case is going to be angle, and angle is equal to average velocity times the time and measured in radians. Before we had average velocity is equal to initial velocity plus final velocity divided by 2, or distance over displacement over time. And here you could also, I should have said average, and here is average. So here I can do the same. Average angular velocity is equal to initial plus the final divided by 2, or again it is the displacement, angular displacement over time and measured in radians per second. You also had a final velocity formula if you have the distance and acceleration combination. So that would be the square root of 2AD plus initial velocity squared. Here you also can have final velocity found by the square root of 2 acceleration, the distance, and plus initial velocity squared. Before we had linear momentum is equal to mass times the velocity, and here we also will have angular momentum is equal to, we don't have mass here, so we're going to have inertia, and inertia changes when we get to torque. I'm going to explain that one more. Angular velocity. Before we would have for linear energy, we would have kinetic energy is equal to 1/2 mv squared, and for kinetic energy rotational, also when we do torques, we're going to come back to this. So its rotational energy is 1/2. We don't have mass, we're going to have inertia, and inertia have different formula for every single type of a body, and angular velocity squared. So the formulas are the same, they're just written differently, and sometimes they seem to be more confusing than they should be, but they are the same formulas that we used to. Also, the time is equal to the distance over average velocity, but in a circular motion the distance is the linear distance is 2 pi r over the average velocity, or you can say the average velocity around the circle is equal to 2 pi r divided by the period, which is the time takes to travel around the circle. So here I can say the time takes to travel around the circle. The same is going to happen for angular velocity. So you can say angular velocity is equal to 2 pi is the angle traveled around the circle one time, one full revolution, and over the time. So the time, the period is to make one full revolution. So period is the time that will take to make one full revolution, is equal to 2 pi over the average velocity, angular velocity. So you see this formula. So far I explained these formulas to you, and let me explain the ones on the right. So let's say a point, the purple point went from one position to another position, and it moves some distance s for some angle. So I'm gonna call it theta. So for theta, I will move some distance. I'm gonna call this distance s, some distance s. But if I go from this point all around, then my theta becomes 2 pi. That's the angle. And in this case, I move the distance of 2 pi r. So if I want to find the relationship between s and the angle, then I will say that proportion of this angle over 2 pi is the same as the proportion s over 2 pi r. Because if you just increase the path this much bigger, then the proportion between them is still equal to. So what I have is theta over 2 pi is equal to s over 2 pi r. Now, if I cross multiply them, I have, and I can cancel 2 pi from both sides. It's the same as multiplying both sides by 2 pi. And so what I get is s is equal to theta times r. So explanation for this formula is the linear distance depends on the angle and the radius. And this is how I can explain this part. If I had a point here, the blue one, and the point right here, do you see that the linear distance for this radius, like if this was a circle, for that radius circle is smaller than the linear distance in purple for this circle. So the linear distance s is proportional to the angle and the radius. The bigger the radius, the bigger the linear distance the object travel for the same angle. Now I'm gonna do something else tricky. So this is the relationship between linear distance and angular distance. So your linear distance is equal to angle times the radius times, so I'm going to rewrite it this way, the radius times the angular distance. So first formula. Let's divide both sides by t. S divided by t gives me average velocity. And that, if I divide the other side by t, I have r, and omega divided by t gives me average angular velocity. And then I'm going to divide both sides again by t. Change of the velocity over the time will give me acceleration. So acceleration, linear acceleration, is equal to, and then again r is going to stay, and divide the angular velocity over the time will give me angular acceleration. So I found the relationship between the linear and the angular displacement, velocity, and acceleration. This is very important. These three formulas are very important because they appear from time to time. I like to think about these formulas this way. Linear distance and angular distance are proportional, but they depend on the radius of where you're looking at, like the blue line and the purple line in the picture. And again, your angular velocity or linear velocity and angular velocity have also proportionality. They depend on the radius. So the bigger the radius, the bigger the linear velocity for the same angle. And one more formula left to derive. So we went through these formulas. And one more formula to derive is centripetal acceleration. Centripetal acceleration is equal to v squared over r Now I know that v is equal to r omega and all of it squared, we just derived this formula, over r. So that is equal to omega squared r. So your centripetal acceleration is actually equal to omega squared r if you don't have linear velocity and you want to plug in angular velocity that you just found. So you could use that formula for the centripetal acceleration as well. Another part that you should know is the direction of angular velocity and angular acceleration. You can see it from our graph right here. So here is the angular acceleration direction, and here is the angular velocity direction. And it is the right-hand rule. And when I say right-hand rule, I mean like this picture that is shown right now on the screen. You see the black arrow is showing the direction of rotation. So you rub your fingers with the direction of the rotation, and your thumb is sticking up. So the way your thumb is pointing is the direction of the angular velocity and angular acceleration. So this would be the direction of angular velocity, and this would be the direction of angular acceleration. And to find the direction of the angular velocity and angular acceleration, you have to wrap your fingers around so that you see they follow the direction of the motion, the black arrow, and your thumb will always point and show you what direction the angular velocity and acceleration are. Let's look at our first question in this section in angular velocity, and it's all about getting used to the new formulas. The questions are not difficult. It's all about getting used to what the new formulas are about and what information is given. So here I'm gonna do it slower so you understand it better. A compact disk rotates from rest. So from rest, I mean initial angular velocity is 0 radians per second. And with the angular speed to an angular speed, so the final acceleration velocity is given angular velocity, that is 31.4 radians per second. In time, so they give you the time it took, which is 0.892 seconds. The question is, what is the angular acceleration of the motion? So the angular acceleration is change of the angular velocity over the time. So that gives me 31.4 minus 0 divided by 0.892 and equals to 35.2 radians per second squared. Next question is asking you, through what angle does the disk turn while coming up to this speed? So through what angle? Angle, that means they asked me about the distance traveled. The distance traveled is average velocity times the time, because the angle now is my distance, it's angular distance. So I have initial velocity plus the final velocity, angular, divided by 2 times the time. And that gives me the angular distance that it travels is equal to 14 radians. And then they ask you if the radius of the disk is 4.45 centimeters. So the radius is given 4.45 centimeters. I have to remember that centi stands for -2. Find the final velocity of the microbe riding on the rim of the disk, and they mean linear velocity. So I know that the linear velocity is equal to r times angular velocity, so linear average velocity, or I can say final linear velocity is equal to r times final velocity. So if I plug in the numbers, then I have r is 4.45, 10 to the -2 because it's centimeters, and the final velocity is 31.4. So the final tangential, oh, the T stands for tangential, because if an object is moving in a circular motion, and so let's say an object went from this point to this point, then the velocity tangential was in this direction, and then the velocity tangential is in this direction. So they ask you to tangential velocity or linear velocity. So if I plug in the numbers and do my calculations, then I will find that tangential velocity is equal to 1.4 meters per second, or tangential final velocity is 1.4 meters per second. And the next question, they ask you, what is the tangential acceleration of this microbe? So I can find tangential acceleration by using angular. So I could use it as before, like from this formula that we derived earlier. I could say tangential acceleration is equal to r times alpha, and I just found alpha, so I'm gonna plug it in, and I have tangential acceleration is equal to r is 0.045, and tangential and angular acceleration is 35.2. So I can find the tangential velocity or acceleration, tangential acceleration is equal to 1.57 meters per second squared. Or I could use information from here. I can say tangential acceleration is equal to change of the linear velocity over the time. Your final velocity is 1.4, your initial velocity was at rest, and the time it took 0.892. So tangential acceleration is again equal to 157 meters per second squared. And I should have said 445, so I missed a 4 right here in my tangential velocity. It's 0.0445 because it's 4.445 centimeters. Here's another question. A potter's wheel rotates from rest to 210 revolutions per minute in a time of 0.75 centimeters. So initial angular velocity is equal to 0 radians per second, and the final velocity, angular velocity, is equal to 210 revolutions. So it makes 210 angles of 2 pi over 60 seconds. So I can cancel 10 and 10, and I can divide by 2 and by 2. What's left in the denominator is 3 right now. So that gives me 7 pi, because 21 divided by 3 is going to be 7 pi radians per second. So this is my final velocity, and this is my initial angular velocity. Then the question is, what is the angular acceleration of the wheel during this time? So angular acceleration is the change of the angular velocity over the time. So I have 7 pi minus 0 divided by 0.75, and that is equal to 29 radians per second squared. So 29 radians per second squared. Then the next question, they ask, how many revolutions does the wheel make during this time? So I know that one revolution makes the angular distance of 2 pi. So that would be one revolution. And I need to find out how many revolutions will happen over 0.75 seconds. So I need to find what distance I travel, angular distance, which is angular linear average angular velocity times the time, and angular linear velocity is 0 plus 7 pi divided by 2, and the time is 0.75. So I will get the angular distance that the object moves over 0.75 seconds is equal to 8.24 radians. So this is what it moves, but in one revolution it's 2 pi. So if I take 8.24 divided by 2 pi, that will give me how many revolutions the object actually made. And I get 1.3 revolutions happen in 0.75 seconds. So the Potter's wheel was started from rest and had no revolutions per second at first, but in 0.75 seconds, it was moving at 210 revolutions per minute. Does not mean it made 210 revolutions in that time. It will make 210 revolutions per minute if it was moving at this moment for 1 minute. But because there's acceleration, it's always changing. So in 0.75 seconds, it made only 1.3 revolutions. Here's another question for our practice. Let's write down wherever is given, and I'm gonna let you write it down on your own at first. Pause the video, and then I'm gonna write it down, so when you unpause the video, you will see already my given data, and then we're gonna think about which formulas to use. And I think you already understand kind of how to use the formulas because you already know kinematics, and this is just the same stuff but just written differently. So try to solve this question on your own as well. So here I wrote everything that is given, and they ask you to find if it starts from rest, what is the angular distance after 18 seconds. So linear velocity is equal to final and initial linear velocity plus the acceleration times the time. The same for angular, so angular final velocity is equal to angular initial velocity plus the acceleration times the time. So I'm gonna plug in my numbers, and I get 0 plus 0.35 times 18 seconds, and that will give me 6.3 radians per second. So this is the final velocity. If I want to find angular distance traveled, I need again angle is equal to average velocity times the time. So initial is 0, final is 6.3 divided by 2, and the time is 18, so that's the same as 6.3 times 9 if I divide 18 by 2, and that will give me 56.7 radians. So that's the answer for A. And what is the angular speed at which the wheel was traveling? So I found the speed and I found the angular distance or displacement. Here's another question that I want to go over with you, and let's do write down everything that you see is given, and then try to solve it first. And then I'm gonna do the same. I'm gonna write down. I want you to start to be solving the formulas that you just learned on your own and understand how much you understand what you're just learning. So go ahead and pause the video and see if you can figure this out. So I wrote what is given, 700 revolutions per minute. So it's 700 of the angle that is 2 pi, because 1 revolution is 2 pi. So 700 2 pi over 60 seconds. And then I have 3,000 revolutions per minute. So it's 3,000 of 2 pi over 60 seconds. And so I simplified both of them, and I got initial velocity of 70 pi over 3, and the final velocity angular is 100 pi radians per second. And they ask you average angular acceleration. So angular acceleration is equal to change of the angular velocity over the time, which is 100 pi minus 70 pi over 3 divided by the time, which is 3 seconds. So that will give me 80.2 radians per second squared. Here's one more question that I want to look with you at. And at time equals 0, the object starts, or the mass starts from rest and falls with a constant acceleration of, not constant speed, acceleration of 8 meters per second squared. When the mass has fallen 1 meter, determine the magnitudes of angular velocity and of the pulley. So they give you acceleration, they give you the distance. So I can say linear velocity is equal to, the final velocity is equal to the square root of 2AD plus initial velocity squared. So I have 2, acceleration is 8, and the distance is 1, and it started from rest, so the initial velocity is 0, so that gives me 4 meters per second. But they ask you not linear velocity, they ask you angular velocity, and linear velocity final is equal to r angular final velocity. So the angular final velocity, so that's again that formula that is important to know. It's not given on AP exam. You have to understand where it comes from. So that is equal to the final velocity divided by the radius. And the radius is given right here on the top. It's 100 millimeters of 0.1. So you have 4 divided by 0.1. So the final angular velocity is 40 radians per second. And the next question B, they ask you to find tangential and normal. And normal means centripetal or rotational components of acceleration of the point at the outer edge of the pulley. So we know that tangential acceleration is already given. It's 8 meters per second squared, so we don't have to find that one. But the normal acceleration, so the normal or centripetal is equal to v squared over r. And we have v is 4, the final, at that moment. So that is 16/4. We found it right there. And divide by the radius, and that's 0.1. So that gives me 160 meters per second squared. And tangential and centripetal acceleration still have the same meters per second squared. That will conclude our introduction to angular velocity and acceleration, or angular motion video, and I will see you in the next video. And again, the links for the next video or the previous video are in the description. So see you later in the next video.